Thanks everyone for joining our talks today. This is our first time in American, so we're a little nervous. So before we start, we would like to thank these people, the original author who developed the algorithm. Everything we have done is built on top of their work. Without them, Sniffer BloodHound would have no idea how to sniff. So big thanks to these people. So let's begin today's talk. And hi everyone, I'm Jiun-Ming Su. I'm a gamer, researcher, and a dog lover. And this is my cute Pomeranian. She is sitting on the top of my brother's laptop. So cute. And my main research area is identity-related attack techniques like AD, ADCS, Entra, and so on.
Hi, and I'm Maxine. I'm homebody, and I'm staying home at almost all the time. And my main focus research is about machine learning and how to apply machine learning on cybersecurity field. Yeah.
So I want to start the talk with the quote. Defender thinks in lists, attacker thinks in graphs. As long as this is true, attackers win. This quote comes from a blog post by John Lambert, now VP at Microsoft. This is a line that has changed how many of us see modern defense. And this quote was also the opening line of BloodHound's first DEF CON talk. Let's Talk on DEF CON introduced a practical way to apply the idea from a quote into a tool, a method, and a community. So today, I want to follow the same spirit. We will take the idea, thinking in graphs, and explore how we can make it even more actionable, not just for attacker, but also for defender too. Ever since the idea, thinking in graphs, was introduced, a bunch of tools have come out to turn security problems into graphs, like BloodHound, StoneSpotter, AdLaunch, AppMan, and so on. But today, let's focus on AD. In most AD graph tools, abusable permission and misconfig, aka identity snowball attack, are turned into graph. And here's a quick recap to identity snowball attack. As you can see in the picture below, if Maxine has permission like write property over Jiun-Ming and Jiun-Ming over admin, the privilege will roll like a snowball like this. Eventually, Maxine can gain control over admin. And these tools are powerful because they reveal indirect relationships. By graphing AD environment, defender now can identify risk like unexpected privilege escalation or other abnormal behavior like hesitation and so on. And take the picture below for another example. If Jiun-Ming is a IT and have legitimate access to admin, then this age is fine. But if Maxine, a low privilege user, somehow gain a path to them, we should be concerned. In that case, we would likely want to cut the relationship between Maxine and Jiun-Ming, and that sounds a little hurt. And this tool successfully turned defender thinking into graphs. Sounds like all the problem is solved, but actually, that's just the beginning of the new set of challenges. So what challenges do we face when analyzing AD graphs? And the first one is, graph is way too big. How this challenge affects our analysis? We can see the graph. We call this challenge as analysis death loop. The first stage, we start with a big graph. And this stage, data is hard to collect, hard to process. But BloodHound already does a great job here. It's able to quickly handle large amounts of relationship data with impressive performance. Then comes the second stage. try to identify bad edges in the massive graph. And as expected, the size make analysis extremely difficult. Then 3 hours later, the analysis is done. You finally find an edge worth blocking. Let's lead us to the third stage, reporting these risky edges to the customer. And finally, after discussing with the customer tells you that this edge is actually essential for this domain, and you can block it. And at this point, you realize we are back at the beginning of the loop. That's our first major challenge. Even if we get lucky and identify a risky edges on the first try, and even if the customer agrees it's not a expected behavior, there's still no tools to measure the actual impact of blocking it. Let's bring us the second challenge. We can't be sure this is the best strategy. We've all been there. Limited time, limited people. So we must be smart about what we spend our effort. That's why we focus on critical edges. The one that can block multiple attack paths with a single cut. Instead of reviewing every possible path, we work with the customer to identify the edges that actually matter. Let's look at the example. If we block this edge, the user still can reach admin through other paths like this. So we have made a change, but the risk is still there. Now, if we block this edge, suddenly the low privilege user has no remaining path to admin. And by focusing on these high impact edges, we can make smarter decisions with the limited resource we have. So now the real question becomes, how do we actually find these critical edges? The challenges we mentioned earlier bring us to the goal of Sniffer BloodHound. First, it needs to handle everything we talk about, like efficiently analyzing large AD graphs, identifying critical edges, and more. But just solving the technical problems isn't enough. We also want it to fit seamlessly into BloodHound's daily operations, so users don't have to change the way they work. It should also support analysis methodology, like full path analysis, and adapt to how analysis actually approach problem in the real world. By the way, this Q sniffer is generated from Adobe. With this goal in mind, we can now break down the key question we need to solve. First, how do we turn an AD graph into something we can actually compute on? Second, once we have computable graph, how do we identify the critical edges in the graph? Even if we can find it, can this process be done efficiently? Because we don't want to spend entire day just waiting for a result. Also, can we ensure the algorithm produce consistent results, not something different every time we run it? So actually, the first three questions has already been solved by the paper we mentioned earlier. What we have done is extend the algorithm to better match real-world analysis needs. And finally, once we have all of this, how do we integrate these things into BloodHound without changing their existing workflow? So with these questions in mind, let's take a close look how the original paper and our enhancements solve each of them in detail.
Okay, now let's move on to the algorithm that powers the core of Sniffer BloodHound. And this section will work through the main goal and the key logic of the algorithm, and so that you can better understand how it helps you analyze the defend and your AD environment. Okay, for the first part, I will introduce how to generate our problem into a graph problem. We first generate the entity to node in graph. And as for ages, I want it can be generated to something like represent the likelihood of being attacked. And with this idea in mind, we generate the exploit codes from BloodHound into risk score and assign the risk score to this relationship. And exploit costs represent how it is for the attacker to attack the relationship, and the easier for the attack, the lower the cost. In other words, when the cost is lower, the attacker is more likely to launch an attack on this relationship. So, which means the age is riskier to be attacked, and we map this relation by assigning the lowest exploit costs. For example, in this generic, the cost is 1, and we mapped it to 0.6 as a risk score. And yeah, we mapped this relationship by assigning lowest exploit cost to the highest risk score. Yeah. And by processing each age using this method, we can convert the AD environment into the mathematical graph structure. Next. Okay, we now have the AD environment graph. Next step is to define a goal. And I will define some special node in graph. Entry node refers to where the attacker can launch the attack. And target is the attacker's goal, which represent like the managed account AD tier 086. And with above two nodes, now we can portray the attacker's attack path as the connection between this entry and target node in the graph. Okay, like this. And the risk score of all ages multiplied together will become the score like 0.95. So this is the score of this red attack path. Yeah. Since the manpower and resources for defense are limited, so we also take the budget into account. For example, we set the budget to block at most 2 ages in this case. So with the budget, the defender's objective becomes to identify the optimal blocking strategy on their limited budget, and then to minimize the risk score, like 0.95 in this case, on the riskiest attack path. For example, given the budget of 2, I apply strategy A by blocking 2 ages. And under this strategy, I got a risk score of 0.4. And in comparison, strategy B leads to another risk score, like in this case, 0.8. So therefore, strategy A is better than strategy B as it reduces the highest risk path score from 0.95 to 0.8 in this environment. Okay, here's another example. With a budget of 1, blocking the first age still leave 1 attack path, like this red attack path. But blocking a different age can stop all the paths at once, so it's a better choice. And we want the algorithm to make the best use of the limited budget for the most effective defense. But unfortunately, this problem turned out to be an NP-hard problem. Yeah, so to better understand how to approach this complex problem, we can start it by analyzing how the blocking decision behave in different situations. So when we'll think it complicated, Well, by observing the blocking decision-making process, we discover things will get complicated when we face this special structure called splitting path. And the path above is a splitting path, which means there is a splitting node in this path, and there's more than one path extending from this node. In this case, 2 paths extending from this node. And the problem for splitting paths is when I have only one budget, and I use it to block one edge, and my defense will be useless when the attacker chooses another attack path. On the other hand, a non-splitting path means a straight path. Wherever the attacker is, my defense on this edge will always work. So in summary, we prefer the non-splitting path to splitting path since we only need to block one edge to block the attack. So the problem becomes how we turn the splitting path into non-splitting path. And the algorithm also introduced a solution by using splitting path as a breakpoint to split the splitting path into non-splitting paths. So in this case, you can see we use the split node at the breakpoint, and we break the splitting path into 3 different colors of non-splitting paths. And for each non-splitting path, we just need to block one edge to block this non-splitting path. Now, by breaking the original graph into multiple non-splitting paths and multiply by the risk scores of edges in each non-splitting path, so we can successfully simplify the goal, like simplify the graph into this. So it also largely reduced the time complexity of the original analysis. Now we have finished explaining the graph representing step. Let's move on to the core part of our approach, the linear programming algorithm that drive our blocking strategy. And before we start, there's a super quick idea of what linear programming is. And it's a math tool that helps us to make the best decision under some limits. So we give it a goal like lowering the risk score and some rules like we can only block few edges, and then it helps us to figure out the best way to reach the goal and at the same time following the rules. So let's see how we apply this blocking strategy. To do that, we define 3 constraints. And for the first constraint, we model how risk flows through the graph, and after pre-processing, every node in the graph is assigned to the value represent its risk score, which intuitively means how likely it is that an attacker could reach the target from this node. Then for every parent and child, we ensure that the parent's risk must at least as high as the age risk times the child risk. So the constraint ensures that each node risk score reflects the highest risk path from that node to the target. So this is the first constraint 1. So you can see this splitting node must be greater or equal to 0.8 is the age between it and its child, and the risk score multiplied by the child risk score. And there is an X, and X means whether this age is blocked or not. Okay, then it's constraint 2. We define the worst case entry for the defender, also the best entry for the attackers as the node which the highest risk score among the entering points. So this captures the worst case scenario, the path the attacker is most likely to success on. And third, we add a budget constraint. We assume that we can only block the limited numbers of age I mentioned earlier, and based on real-world constraints like time or resources. objective is not just to reduce the score in general, but specifically to minimize the best entry value, which represent the best attack path is the attacker can take in the environment from some entry point all the time to the target. With the goal and C3 constraint, we can set about a linear program and let the solver to find out the best way to assign risk score and choose which edges to block to make the attacker's best pass act as weak as possible. Okay, from the result of the linear programming, we can get the risk score of each edges. Not edges, but nodes. We can get the risk score of each node. That is the probability of most dangerous attack paths from each node to the target. That is also tell us which entry point that has the highest risk score. In this case, this best entry is the entry point that has the highest risk score. So we start from the most dangerous entry node and try to trace the riskiest attack path from here. In this case, both the top and bottom paths are blocked and no longer be used. That means the attacker can only has the green path left. By following the risk score step by step, we can infer at each node which incoming edge contributed to the score by repeating this process until we reach the target. We construct the most dangerous attack path under this blocking strategy, which in the end is this blue line. Some people might wonder what if we have more than one target node. In this case, we can introduce a virtual target node, and we connect this virtual node to all the real node target nodes using special edge that cannot be blocked and have the risk score of 1. So in this way, we can treat it as a single unified target using the optimization process. Okay, that's it. That's all the core algorithm about Sniffer BloodHound.
Oh, and thanks to Maxine for that amazing walkthrough of the algorithm. So now let's talk about Sniffer BloodHound and how we put everything together into a framework. As we mentioned earlier, Sniffer BloodHound is built entirely around the algorithm. So we decided a flow that allows us to run the algorithm directly from the BloodHound's UI. And thanks to the SpecOps dev team and their hard reloading feature, we were able to add a few custom buttons to UI super easily. Oh, sorry. Now, when you click the new button, you can think these two dogs are talking to each other with Fast API, Selenium, Python, and Neo4j instead of just Woof Woof. So, let's see the real workflow. First, we write a short script to automatically monitor what cipher queries does user input. Then, output queries itself into raw query text for algorithm use. Now, when the user presses the newly add button, it triggers Fast API that runs a two-stage program. The first stage is using Selenium to send the cipher query to Neo4j and extract the relationship from the graph. Then, the second stage is where the algorithm kicks in. It takes the relationship data, calculate which edge should be blocked, and then output the result into BloodHound's UI, and that's the full workflow of how Sniffer BloodHound work. And during this research, we also realized something interesting. The block edges and full paths actually contain a lot of useful information for both attacker and defender. So we started exploring how to make use of this information. On the defender side, we generate a report like this. A plan that shows you why you should block these edges. You can even enhance it using LLMs to make it more readable. On the attacker side, we convert the data into a format that auto attack tools like AutoBloody can understand, something like this. But these features are the main focus of our work. Also, we only have 2 people, just Maxine and I. So what we build is just a quick prototype, more like a proof of concept at this stage. Now let's see what happened when we actually put Sniffer BloodHound to work. In case study, we test Sniffer BloodHound on 2 simulate environments. The first one, we had about 100 nodes in this domain, which is quite small, but still enough for a quick proof of concept. Then we run a query from all shortest paths to tier 0 assets. Here's the resulting graph. It contains around 30 nodes. And this video demonstrates how Sniffer BloodHound works. First, we run a pre-built cipher query to show all shortest paths to tier 0 target. And wait a second. And as you can see on the right side, once we execute the query, our scripts automatically capture it in real time. And for the final step, when we click the newly add button, like this edge blocking, this edge block button is our newly add button. When we hit start, and boom, within a second, the algorithm output the results into BloodHound's UI. And let's check this result. Here's are the blocked edges recommended by the algorithm. For edges 1 through 6, we usually need to review the full path to see whether they are the part of normal situation. And some edges like GP-link from the default domain policy are usually expected, while others like H7, ADCS escalation 1, looks most suspicious and worth discussing with the customer. So how do we dig deeper into this path? Let's look at how we use full path analysis to make that process more effective. As Maxine mentioned earlier, we also support full path analysis. We try to show the full path in the UI, but trust me, it looks terrible. So to make the analysis more complete, we export the full path into 2 CSV files. One shows that the request attack path before blocking, and the other one shows that what's left after blocking. So inside this full path CSV, it will include the probabilities and the entire attack path behind each edge. Let's go back to that GP link example. The full path shows that the source of the edge is the group parse itself. Just by reading the CSV, we can quickly mark it as unblockable. Still, you could inspect the GPO contents just to make sure there is nothing malicious inside. Look at this other case. DC01 is a member of domain controllers. Again, something we would never want to change. And this kind of detailed path analysis help us review edge decisions with more context, especially when we dealing with a large number of results. And in case 1, the environment is relatively small. So once we block those 7 edges, all attack paths disappeared from this graph. But in large environments, that's not always the case. Even if we block 50 edges, we might still see some attack paths remaining on graph. And that's exactly where the after blocking CSV become helpful. It's highlight the weakest remaining paths and help us to decide what to prioritize next. So let's wrap up our first simple case study. Now let's move on to the more complex scenario. One where we apply the same approach in a much larger, messier environment. And the second one is bigger than the first one. And these are 300 nodes in this domain. And again, we use the all shortest path to theory raw assay query. And here's the graph, around 150 nodes. As you can see, trying to analyze a 115 nodes graph at a first glance is not easy. Alright, let's speed up the demo a little bit. Just like the first demo, the query runs fine, fast API responds correctly, and yes, the output is still a bit ugly, but the response is still fast, and everything's work as expected. So let's check the results. Now this one is a bit more interesting because this is the environment I usually use to reproduce real-world attacks. Here, Edge 1 and Edge 2 are related to ADCS escalation setting attack. And just by looking at the edge type and the edge name and the name of the source node, we can already tell these edges should be blocked. And for edge 3 through 6, we need to take a closer look at full path to see whether they are part of normal operation or something suspicious. Then we have edge 7 through 9. These 3 has session edge pointing to the domain controller. These are perfect example of why we can quickly bring to the customer and ask, is this expected behavior? And if not, they can be marked as a candidate of blocking. Now, let's take a look at the full path analysis before blocking. Here we see a domain that contains a user, which sounds normal. But when we check the full path, we notice there's a GPO links to the domain through GP link. This is where we need to take a closer look. Is this GPO actually supposed to affect these users? For example, there's one GPO called test11. It might have been created for testing, but later forgotten. That's something we can discuss with the customer. And these small details are hard to catch without full path analysis. And now let's take a look at what full path looks like after blocking. And just like the last graph, after blocking these 9 edges, there's no remaining attack path in the graph. So at this point, Sniffer BloodHound has done its job. It's helped us to identify the critical edges, validate them, and block all known paths to tier 0. But of course, no tool is perfect. Let's take a moment to talk about some of the limitations and drawbacks we encounter while building and using Sniffer BloodHound. So what's the current limitation of Sniffer BloodHounds? First, the output is still a little ugly. It shows the result, but it lacks more user-friendly formatting or visuals. And second, efficiency can be a concern under certain conditions, especially with large graphs, complex structure, or higher risk budgets. If you are interested in efficiency, the original paper provides a detailed evaluation table. They generated around 40,000 edges using DB Creator and AD Simulator and tested the algorithm on that data. And the result was surprisingly good. It returned the result in under a second. And third, we still need to manually define each edge's risk score. But risk is hard to express with just a probability. Assigning a single value can sometimes distort the whole graph. And finally, there's the issue of unblockable edges. In many real-world cases, we don't know which edges can or cannot be blocked until we have discussed them with the client, like what the analysis Deathloop talk mentioned. So we still need to tune back and forth a few times, manually updating the unblockable list. The good news is, even with 40,000 edges, the algorithm still perform well. And finally, let's talk about the future work. And first, and most importantly, a better algorithm. One that can handle even larger environment and work with three unliked AD graph, which are common in the real world. And second work can be done in containerized Sniffer BloodHound. So it can be fully integrated into the BloodHound architecture, make the workflow simpler and easier to deploy. And the third one is we want a more beautiful UI to give user a smoother and more intuitive experience. And lastly, we want to keep thinking like both attacker and defenders and add feature to make everyone's life easier, like an LLM powered report module or even a auto attack module. And that's it for today's talk. And thank you all so much. And
all right. Thank you, Maxine. Thank you, Jimmy. We have a little extra time for Q&A. Tell me, who's got questions? And please use the mic. Rohan, you're first.
So early on in the presentation, you referred to, for each edge, you have a risk score as well as a cost.
Yeah.
How did you determine those costs? Was that from the white paper or was that from your own practical experience?
That is a random decision.
Okay.
Yeah. Yeah,
All right.
we don't do lots of research about the numbers, how to transform from the exploit cost to to the risk score.
Okay, and then the other question I had was like, how when you scale this up, like, what is the exponential cost increase between like a smaller environment, like the ones you're using, as compared to like a true AD environment that would have like maybe 200,000 or 300,000 nodes? Have you like, what's the biggest environment you've tried this in?
What's the biggest environment? Yeah, I think the biggest one is 1,000.
Okay.
Yeah, just 1,000 of computers. Yeah, but for time complexity, you can calculate it by when you after pre-processing, you can calculate how numbers of non-spin paths. You can calculate the number of non-spin paths, and that decide. You can kind of evaluate from the numbers of non-spin paths. So it's kind of, if you have 1,000 and it takes 0.5 seconds, and if 5 times larger, if the non-spin path amount is 5 times larger than the thousands, maybe 5,000, maybe the time will be 5 times around. Yeah.
Okay, cool. Thank you.
Other questions? Go.
Thank you. It seems like the remediation of each edge subtracts from the budget equally, unlike the risks that have their own risk and their own costs. Is there any thought about assigning a unique value to remediating each edge?
You mean the budget or the weight?
The budget, where like you feel have a limited budget, so the more you have to remediate, the more budget's going to take up.
Yeah, actually, there is an advanced algorithm based on this basic algorithm that you cannot. Your budget is not only 1 or 0 for each edge, blocked or not blocked, but you can assign the probability to the budget. Yeah, but the math is more complex and it's more. It has a lot of things that hard to explain. So yeah.
Sure. Okay. Thank you.
Maxine, Jimmy, again, thank you so much for being here today.
Thank you.